welcome everyone. So today I'm alone because everyone has a meeting to attend. So I will try to do everything right. So just a few words. As always, we manage the Grace Code Thursday. So today we will talk about a bit of wizardry with C++ and STD algorithm, Cuda, thrust, and stuff like this. So I will give you an overview about everything. And of course, you are still able to register to the school. So we are around 200 attendees for now in the school. There is some places left in Annecy if you want to attend the school in person in Annecy. But of course, you can register for wider overview. So you can have a satellite site, you can register just online, depending on what you want to do. So don't wait too much, because at some point, especially if you want to go in Annecy, at some point the registration will be quite full. But normally now it's a bit okay, but since it's quite difficult to have an apartment or an hotel in Annecy during this period, and of course we ask you to give us some information if you have an hotel, because if you register but you don't have an hotel or you cannot attend, it's not fair for the other participants who want to attend the Annecy. So try to do that as soon as possible if you are interested to attend the school in Annecy. So we have a trailer to explain that for you.
Could a simple chemical reaction teach you how to unlock peak performance on today's supercomputers? Welcome to the Gray Scott School 2026, a free advanced summer school on high-performance computing, designed for professionals from industry, public sector organizations, and academia. From June 22nd to July 3rd, 2026, join us in Annecy, France at LAPP, at one of our satellite sites across Europe, or online via live streaming. All courses are taught in English. You can pick the courses most relevant to you or dive into the full 2-week program. You'll learn the practical behavior of modern hardware and how to write performance-optimized portable code. Week 1 focuses on CPUs, Week 2 on GPUs, covering architecture, bottlenecks, parallelism, memory, and performance analysis. All learning is built around a single challenge: simulating the Gray-Scott reaction. Simple to start, yet complex enough to stress compilers and expose performance limits. You'll explore modern tools, languages, and libraries such as C++ 17 and 20, Cuda, Fortran, Python, OpenMP, TBB, Kokkos, PyTorch, and more. The school provides ready-to-use container environments for smooth hands-on sessions. Expert instructors from CNRS and CEA guide you with live Q&A and community support on Discord. Satellite sites let you learn together locally without traveling. Want to host one? It's easy with our turnkey setup, sharing the school with your colleagues and ecosystem. You'll leave not only with hands-on HPC skills, but also an official certificate of participation. And you know what? You can start early with 18 Gray Scott Thursdays webinars, weekly from January 29th to June 11th, introducing summer school concepts and new topics. Whether you're an industry professional, engineer, researcher, or student, if you have programming experience and want to push your skills further, this program is for you. Register now at cc-fr.eu and start learning today. Gray Scott School 2026, Europe's leading HPC summer school.
And of course, if you have some question regarding the registration, regarding if you want to get a satellite site, if you want to host a satellite site, or you know some computing center or some auditorium and you wanted to attend here, please contact us. So Karim, Marie, or me, and we'll make sure that everything will be okay and on time also for you to follow in the satellite site you want. No problem. Now it's time to do some wizardry with modern C++ on GPU. So with STD algorithm, as I presented a couple of weeks ago with CPU. Here we will do the same on GPU. We'll have also some Cuda and some thrust to have the comparison of what we want to do, what we don't want to do, some insight also to visualize what's going on. So without further ado, let's jump right here. We'll start as the last time, in fact, on this topic. So remember, I was talking about standard C++, so for CPU and for GPU. And if you want to do some CPU computing, you can use TBB, so threading building blocks, parallel library of Intel. If you want to do some GPU computing, here we will have some thrust and some Cuda today. But you can also use a lot of libraries. You can use Kokkos, Alpaca, SYCL, OpenCL, OpenSCC. So they do a bit of both, and you can pick the one you want. So here we'll do a thing a bit differently. Here we will have use of compilers directly, so G++ and Clang++. And with these compilers, you can directly, in C++17, do some magic with STD transform and recall directly TBB, which is really, really powerful. And since late 2020, November 2020, it's possible to do the same with NVC++ and NVFortran, as Vincent mentioned last week. So here I do some call in C++, standard C++, and NVC++ will figure out how to call thrust for me. And that's what we will explore also today. So first, since we want to do some computing, we want to express parallelism, of course, it's really important, and I redo the slide again. If we start with one event, and we are really lucky, as Vincent said, we have independent event, so independent computing, so a lot of parallelism. It's delightfully parallelism, not embarrassingly parallel, delightfully parallel. You want to be in this case as much as possible to ensure that you have scalability. And especially on GPU, if I have my event, maybe I cannot fit enough event in my GPU to ensure that I start enough threads. As I said before, you have to start a lot of threads to be sure that you use your GPU efficiently. And if I have maybe a couple of thousands of threads in my GPU, it's not enough. It's way not enough. And if I want to increase the parallelism on it, I have to break down my event into pieces. So maybe my events are composed of captors. So I can break down on pixels, on cells, on lines, whatever you have in terms of detector. And maybe it's still not enough. And maybe you want to break down again the pixel into time response, so slices, waveforms, pulses, whatever you have in terms of calorimeter, of pixels, or stuff like this. And then the question is, okay, I have a big cube of data. How do I store them? In which ordering? Which are the ordering of the axis? So to answer this question, I have to ask myself, okay, what I want to do with this data. First step of the analysis could be calibration. So we take some voltages and then we compute a number of photons and energy compared to these voltages to have some physical values, and then we can deal with that later in the analysis. Let's pretend for the purpose of this slide that the calibration is independent in terms of performances. So whatever the ordering, you get the peak performance of your computing. Of course, if it's not good, it's not valuable, but if you have the peak performance, it's okay. So let's pretend that it's okay in every ordering. So in this case, could be a scalar. The calibration involves a scalar. The scalar you can call the scalar in every order you want. It's a scalar, so everything will be broadcast in a nice way. So let's pick the second one. Second one will be an integration. So we want to sum the signal and increase the signal over noise ratio. So I talk about sum So if you heard about sum, you instantly think about reduction and you instantly thought about backdependency. This means that I don't want this cell sum with this one if they are contiguous in memory. Because I will have a backdependency, I will wait for the CPU or the GPU to get back the result before trying to get another computation, and everything is really slow. So you want to be sure that the axis you want to choose is orthogonal to this one. So let's pick this one. So we have contiguous data here. So a full slice of pixels, so a full frame of video if you want. And then we can change the slice to have another slice with a full pixels of another slice. So by doing that, we can vectorize. Sounds great because vectorization and GPUification is really close. So we can also GPUify, and that's what we want to do today. And it's okay for the integration because we did that for the integration, and it's okay also for the calibration because the calibration does not care. And if we do that, the second axis will be this one, because I don't want to be my slices to be too far in memory, so I want to some contiguous slices in memory. And the first axis, if I am row-wise in C++, if I am column-wise, of course, the first axis will be this one. If I am row-wise, the last axis will be this one, depending on your convention. And then the first axis here will be event. And I can parallelize on nodes, on CPU, on GPU, on clusters, on cores, on everything I want. Everything is independent, so no problem. So this is, again, to remind you that computing drives data storage, and you cannot store randomly your data and hope for the best. It's not possible. So you have to understand what you want to do and to be sure that everything is efficient. So that being said, when I talk about Cuda, it's not about only the language, even if we'll see a bit of the language today, but it's, first of all, an ecosystem. So we have libraries to do some kernel development. So we'll see Cuda. We will have also Q++ and Cutlass. So we'll not have the time today, but if you are curious, we can also have a bit of that in the school. And we have library on top of it, typically computing libraries, so QBLAS, QLAPACK, QPBLAS, QScalaPack, QTensor, QSparse, QRound, QFFT. So Martha mentioned some of them also last week. So if you want to do some computing, so classic BLAS computing generally, or FFT or random stuff, it's okay. And then we have Rust, so layer on top of Cuda, if you want to simplify in a more C++ way to call some Cuda. And also we can do some computing and I/O, so with CuPy-numeric, with Legate, with QDF for data frame, if you want to optimize this kind of stuff. And the last part is for I/Os and communication, you have NVSHMEM, you have the GPU Direct for GPU Direct storage, and Nickel. So NVSHMEM point-to-point communication, Nickel is you have ring communication, you have a lot of strategies in communication, and GPU Direct for direct storage, so the GPU can directly read or write in on a disk, for example, on an NVMe, on SSD, stuff like this. You can directly read and write. You have the same also to read and write directly on the network to send and receive messages on the network. So NVSHMEM typically, or Nickel, they are made for that. We will also profile a bit to see what's going on with Insight. And now the good news is we can debug, because in the old day of Cuda, it was really difficult to debug. Now it's much more easier to debug, and it's really, really nice. So first, once I want to compute on GPU with Cuda, I try to unzoom what I want to do. So here, if I take the example to perform a computation on event, for example, so as I said, calibration and then integration and then parameter extraction, stuff like this. I want to unzoom. I want to say, okay, let's not focus on one event. Let's take a big amount of event and see what are the global operations that we can express on this. So this way you can say, okay, if I want to calibrate and I have an event matrix, so for example, each row will be an event in this matrix. if I want to calibrate, it's just a broadcast. So I have my calibration vector here, and I broadcast the vector here to calibrate all the values at the same time, all the events at the same time. It's one operation to treat a bunch of data, really efficient. I can do the same, for example, if I want to do a signal reduction, which is quite common in software analysis. So I have my event of matrix. I want to sum all the values after my calibration to see if I get enough signal, for example. But of course, you cannot reduce on one row. It's not that easy, but you can use some tricks. You can say, okay, I cannot reduce on one row, but if I do a matrix vector multiplication with a vector of ones here, I can reduce all the rows here as I want here. And if you want to have some coefficient, you can also. It's not a problem. You have coefficient and then you reduce with your coefficient. Here you reduce with 1. I just want to have a really simple sum. It's okay. But maybe it's not only that you want to perform. Maybe you want to extract some momenta. So you want the barycenter, you want momenta in superior order to compute the skewness, the kurtosis, the things like this on your image, which is quite common if you want to search some patterns or some ellipse, stuff like this. So you have to think how to do that in a global way. And of course, it's a global way. It's just a projection. So you want to project, you create your matrix of projection for all the momenta you want, and then you do your matrix product, and everything is okay. Good news. And of course, you can do also trick. You can say, okay, maybe I want some masking, because I don't know, I have a camera, I want to extract the border of the camera, I want to extract some cells in the camera, whatever you want to do. Again, it's just masking. So you have a matrix or a vector, depending on what you want, or you have one vector per mask if you want, and then you do your matrix multiplication, and everything is fine. And of course, you see me come. If I do that, I can perform one matrix multiplication for everyone and get all the result at once. So if I do that, I can call, here we will call Kublas today, but you can call MKL, you can call LAPP, you can call whatever you want, and you zoom out your problem and you say, okay, let's put as much as matrix product that I want. And with this particular problem, you don't want to be bothered with, okay, I want a number of events which is a power of 2 because it's better if I do my kernel, or I want a number of pixels which is a power of 2, otherwise my kernel is horrible to treat, or a multiple of 32 because of the warps, and we will see that a bit later. No, just a matrix product. And of course, if you change a bit of padding, you tweak some parameter, maybe you will have a speed up, but globally, you have a big matrix, you want to do big multiplication, and you will be able to use tensor cores directly. So it's really, really efficient to do that way. But of course, sometimes you want to dig into the detail because all the computing you want to do is not possible to express that in a parametric product, but I try to do that as much as possible before entering in the weird detail and before trying to code some kernel, Cuda kernel directly. So once I want to call typically Kublas, I always pass through a little backend just to abstract myself to the compute backend I want. So for example, for SGM, so single precision general matrix multiply, I want to have something like this. So I want to call the Kublas SGM with the handle here and all the parameters you want to use. And to say, okay, I want my matrices, for example, my matrix are row-wise because I'm doing some C++ and everything is row-wise by construction. But sometimes, always practically, the BLAS libraries are column-wise because it comes from Fortran, and Fortran is column-wise. So all the BLAS libraries are column-wise generally. And if you don't read carefully the documentation, you will have to figure out, okay, I have to tell if my matrix is transposed, but transposed compared to what? And it's transposed compared to column-wise. So instead of telling row-wise or column-wise, which is much simpler to understand, you have to tell transpose or not transpose. So I do a little wrapper just to be sure that everything is nice. So if I'm wrong, I can pick and change only at one time, and everything is okay. So I can perform my matrix multiplication with all the nice parameters. I can do some unit testing to be sure that I call this one right. Of course, the result will be right normally because it's already tested, but I want to be sure that I call it in a nice way, in a relevant way. I can do the same also for matrix vector multiplication, so single general matrix vector multiplication here. If I want to project only one vector, could be nice. And to use it, it's really simple. So I can do a type def to say, okay, here I want my cubeless struct here, which contains all the method. I say, okay, cubeless, it's my compute backend, or MKL, it's my compute backend, and then I can pass my SGM with my compute backend, and everything is okay. And if you do that, so it's you do that a bit by hand, but the good point is, if you have a nice performance or on your laptop, for example, you have a small GPU on your laptop, and your boss want to check that, but it doesn't have a GPU on his laptop, you can just change the backend, say, okay, let's use MKL, yes, let's use LAPP, and it's okay. And then you can be sure that everything is okay. You can compare the results also with the two backend. You don't have to rewrite everything to be sure that everything is nice. You just have to change the backend with one type def, and then you are rolling, and it's okay. So quite nice to have this habit. But then sometimes you want to dig into the weak details of the kernel programming, and we will do that right now. And we will have some reminder of the last time, so about thread hierarchy. So briefly, if I start with a thread, the thread will be attached to a core, a GPU core, and we will execute a computing kernel. Then we have warps. The warps are linked to the hardware scheduler, so you cannot deal with that. It's the size is fixed, so it's 32 threads in NVIDIA GPU generally, and you have synchronous execution of the thread. On top of that, you have blocks related to streaming multiprocessors, and then you have 2 to 4 warps depending on the GPU, and it's asynchronous, so you don't have the guarantee that 2 threads belonging to the same block will be executed at the same time. For a warp, you have the guarantee, but for a block, you don't have this guarantee. Then you have clusters for block communication. So with Cuda 12, since Cuda 12, with Aubert, you have this kind of stuff if you want. With Aubert, so you have 132 processors, and with Ampere, you have 108. So one SM is smaller than 1,000 of the GPU. So for block communication, it's quite annoying. So they had the clustering for that. And finally, we have the grid. So this is a full GPU. So for example, Blackwell 10,000 cores, Hopper 8,000 cores, and Ampere 7,000 cores. And then you can deal with that nicely. In terms of execution, you have to remember that one thread makes no sense. So we will deal with warps. And one warp will load execution 2 by 2 and execute instruction 2 by 2. And then when there is a condition, we load the condition, we compute, everyone is computing the condition to see if it's true or false for the particular thread. Then if the statement, the value is true, we'll execute the then statement, and all the other thread will wait politely, even if there is only one, of course. And then the else statement will be executed for the other thread, where the condition is false, and the previous one will, of course, wait politely, because all the threads are really polite. That to remind you that, of course, if you put a if then else statement on your kernel, you will pay all the statements, even if there is one thread to do that. So you pay all the statements for the warp, not for the other, but still could be quite annoying sometimes, depending on what you do. So in terms of mapping, the goal is really simple. You have some cores, you want to map all the data you want to deal with, and then you pass through all your data with the threads, and normally everything is efficient if you do that. So I map the data on the thread to be sure that, of course, you want contiguous data, otherwise you will have a problem. And to map data, I have some information. So I have my thread on a core, my block on a SM, and my grid, which is a full GPU. to get my thread, I have a thread ID to say, okay, I am this ID in my block, this index in my block. For a block ID, I have this ID in my grid, so I can figure out what I'm supposed to do, and I have three-dimensional indexes to simplify the matrix product and the n-dimensional product. But there is some limitation. So for H3000, for example, on my laptop, I cannot exceed 1024 in X, Y, and 64 on Z axis. I cannot have more than 1024 thread on one block. So if I do much more, I will have an error. And I cannot have much more than 1536 thread per SM. So it depends, of course, on the GPU. This is a quite whole GPU now, a small GPU or laptop, so don't worry. But you have to check that on your GPU to be sure that you don't exceed that, otherwise you will have an error. And the same for the block, but the limit is quite high, in fact, here. So you can have a really high limit here for the X, but Y and Z are much smaller, so it's unsigned integer in 16 bits. So you have to deal with that. And at some point, if you want to have bigger block, you cannot have bigger blocks, so you want to increase the number of blocks to be sure that everything is nice. So you have to deal with that if you want to use blocks. Then, which block size? How to determine that? So let's take an Adama product out of 1000 elements. And then if I use 10 blocks of size 100 with a warp of 30 threads, I will have 10 identical blocks, and the last warp of my block will be way empty, and I use only 78% of my GPU, which is not quite good. If I use only 8 blocks of size 128, I have 7 blocks of the same size with full of threads, everything is efficient, and the last one, because 1000 is not power of 2, or multiple of 32 in that case, that last thread will be a bit not really well used, but all the other will be well used. So I use 98% of my GPU with that strategy. So it's important to have the right strategy. In terms of read and write, so I have one sector of 32 bytes in my GPU. So generally I use to read 4 sectors here. So if I have 4 byte elements, so a float, for example, with my 32 threads, I will read 4 sectors. So in contiguous way, if I do things properly in my kernel, of course. And if I do the same for 8 byte element, for a double, for example, I will read 8 sectors. Everything is efficient, and this have to remind you, this is really close to GPU, CPU vectorization, of course, because it's the same ID. Even if here you are in a thread and not in a vector register, but that's the same ID. If you want performance, you have to think the same way. In terms of layout, again, this is really important. If I have my read-write sectors, I assume that I will use a structure of coefficient here of 80 bytes. And then I have in RAID my structure on the memory, on the sectors. And if I want to read the value of U, for example, all my thread will jump in the memory, which is really bad. In fact, even on the GPU, it's really bad. You do not want to do that on CPU, but you don't want to do that on GPU either. And it's not efficient, and I will use only 4 bytes out of the 32 that I will bring in my memory. So you can have a kind of cache crashing, stuff like this, which is really bad for performances. So of course, the right way to do that is to use a structure of array, so SOA, with I explode all my structs in vectors, or in tables here in this example. And I get contiguous data, and if I want to read the value of U, I read the value of U at once with 4 sectors, everything is efficient, and all loaded bytes are used, and I pick also less sector. So here it's only 4 sector for 32 threads, and here it's 32 sector for 32 threads, which is way too much. So let's do some magic with Cuda. Let's start low level, and then we will jump a bit after that. So Adamar product in Cuda, it's an element mass operation, okay? And if I want to do some computation with Cuda, I will have this kind of kernel. So first, I use global to tell the compiler that I want to execute this kernel on the device or on the host, depending on the humor of the compiler. And then I want to compute the thread position to be sure that I will manage the right data into my to my table, because I pass a full table here each time as a parameter. So I want to say, okay, with my block ID x dot x, I get the x value of the block, the thread, the block index. So I have to get the block dimension also to be sure that everything fits correctly, and then the thread index. So here everything is on x axis, but of course you have dot y and dot z if you want to deal with 3-dimension kernel, which is not obvious in fact, but it's really powerful. And then just after that, we just take the value of the vec left and the vec right, do the multiplication, the Adamar product, and then we put the result in the right index. Of course, if you change the index here, you don't want to have two threads writing at the same memory address, of course. Otherwise, you will have a problem. As for the CPU, it's the same problem. So be sure that all your threads do independent stuff. Then I want to call it. I want to call my kernel. So to call my kernel, I can do that. So first, I want to allocate my data on the GPU to be sure that everything is nice. So with the famous Cuda malloc. Then I want also to free my data on the GPU, just to not forget to free once you do the allocation. It's a nice habit to have. And then, of course, here, if I call it once, it's okay, but maybe I don't want to do the allocation inside this function if I call the function a lot of time. So maybe you can move out these calls to be sure that you don't reallocate each time, because allocation, it's costly even on the GPU. It's even a bit more costly on the GPU. So you want to be careful about that also, and minimize the number of allocation you want to do, and reuse as much as possible your memory. So then I want to transfer my data on the GPU. So with the Cuda memcopy, so Cuda memcopy host to device. So I want to copy from the host to the device my vector here. So here you have also a little convention, naming convention, depending on what you want to do. You have vec left D for device and vec left with nothing, or H if you want, for host. So nice way to name a variable to be sure that you are not lost in your kernel, because you have roughly here twice the number of variables that you have in input. So you have to deal with that carefully and be sure that you don't mix them up. Then we want to transfer the results back to the host with the Cuda memcopy device to host call with the same Cuda memcopy here, with the opposite here. So I get the result D and I put that in the result. So the result passed here in argument. And then I want to determine the grid and block size, because you have to do that manually if you are calling Cuda yourself. So here it's not really nice way to do that, but for one dimension is okay. But of course you can do much better if you have time and if you have dedicated function for that. I encourage you also to be sure that you can have that really efficiently, because it's not really easy to do. And finally, once you did everything, you can call your kernel with the famous triple chevron here. So you pass the dimension of the grid, the dimension of the block, and the argument of your kernel, and everything will be mapped to your GPU automatically. And normally everything should be okay. And last trick also, here I have a little macro here, just to check each time I call Cuda function here, if everything is okay. So I check the Cuda error to be sure that there is no problem with the call of this function. And because of course, if you start something, you have an error, you don't deal with the error, you don't have the result you expect, but you don't know why. So it's quite annoying. So at least for once you develop, as Sebastian said in his unit test seminar, you will develop once and you will debug a lot of time. So try to have a nice debugging experience. So this is a nice way to do that. So then, if I summarize, I can have this kind of stuff. So it's not that long. You can manage a lot of things with this kind of approach. Of course, the kernel is really simple, so it's not really efficient. And if I try to do some benchmarking here, so you have the difference between the Cuda kernel itself, so without the copy, of course, and here I have the copy. So you see that, of course, the copy costs a lot at some point here. So I increase the time by a lot because of the copy. And one thing I want to mention here is if you try to pick and to get a bit the performances that you can expect with NVIDIA server settings, for example, here you will get 100% of usage of your GPU, which is nice. You say, okay, that's really efficient. I'm proud of myself, no problem. But of course, if you are here, we'll say, okay, 97%, quite good, but not that good. Then here I will say to you 60%, which is in fact not 60%. If you look at here compared to the difference of the time here, it's not 60% at all. And here it's 22%, and it's not 22% at all. It's normal. NVIDIA server testing is a bit optimistic because of typically you have the sampling once you get the information, and the sampling can have a bias depending of the size and the length of your kernel, the duration of your kernel. So try to be careful with that. It's not generally it's a bit optimistic. So typically here it's not 60%, it's well less. So try to carefully have this information. 100% is nice, but less, maybe it's a bit too optimistic. You have to figure out with insight to be sure that everything is efficient. So then let's do the same with thrust. So my Adama product again, and I can do that with thrust. Much more dense, and I can have my initialization of my vector. So I use the host vector here, vector on the host. Then I can transfer my data from host to device. So here I use a device vector. I use the equal operator from the host, the H, like X, to the D device, like X, with a simple equal operation. So the same as we mentioned last week with Vincent in Fortran. You can do only an equal, and then the transfer will be done for you. So the same ID here. And then you can allocate directly the results on your GPU because you don't want to have an empty result for now. It's not necessary. Then you call your kernel. So the kernel is lambda function here. So with host and device. Maybe I have to figure out if we can put some global here. I didn't have time to check, but if you do host and device, this is clear. And then I call a thrust transform, which is really close to STD transform, of course. This is the same ID. Then finally, I do my transfer device to host with also a simple equal operation. So it's really nice to do that. And you can notice, of course, that I don't have to deal with the size of the block and the number of blocks on my grid. So it's done automatically by thrust. And it's a nice way also if you want to determine with a Cuda kernel which is the best size for your particular GPU. You can ask thrust and say, okay, let's write an equivalent kernel with thrust and just see which is a size that he uses. So it's kind of nice way to get some information. So of course, it is really small, and you can now use thrust universal vector. If you don't want to be bothered with explicit data transfer, you can say, okay, I want to use a universal vector, and if I call a kernel on the GPU, universal vector will copy data on the GPU, and if I call a function on the CPU, the universal vector will copy automatically the values on the CPU for you. You don't have to be bothered with that. It's really, really efficient. So it's really nice to use, in fact. So here we talked about NVCC for Cuda and Thrust. And we still have to tell a bit about NVC++. So NVC++, since late 2020, is able to do some GPU wizardry with std_par. So with C++17 and std_par, I can call directly std transform from the standard library, and then everything will go on the GPU. I have nothing to do. It's really efficient. It's really nice to use. Okay, what's going on? So if I do my Adama product, it's an element-wise operation. I can use my classic C++ for loop with an explicit ordering, but it's not necessary. I already said that. We have the STD transform, but it's not really interesting here. But we have the STD transform of C++17 and C++20, which is really powerful because you have an execution policy. And we'll use that for the GPU computing. So here you have the sec for sequential operation, so a for loop, classically. The unsec for non-sequential, so potentially vectorized, but not only. You have parallel par for parallelize, so with TBB, for example, and par unsec for the parallelize and vectorization, typically what you want to use for recent GPUs. So typically it's Ampere, Hopper, Blackwell. You want to use that. And for, I think it was Pascal, it was only par, because par unsec was not supported, but it was an old one. So now normally should be okay with par unsec. Everyone should be aligned on par unsec. So if I do that, I can export my my compiler. So I use GCC for C compiler and NVC++ for C++ compiler. So with CMake, you are not obliged to pass the CMake CXS compiler. You can just define CXX export, environment variable, and everything will work. And if I call std_par on equal GPU, I will use the CPU, and NVC++ will use, of course, trading building blocks, the parallel library of Intel, because it's really, really efficient and no need to reinvent the wheel. And you want to link with TBB explicitly, otherwise you will have a link problem. So yeah, NVC++ cannot guess where TBB is, and the same for G++ or for Clang++. You want to explicitly link to TBB, otherwise you will have a problem. But if you use NVC++, std_par equal GPU, Thrust will be called automatically by the compiler itself, and you don't want to link explicitly to Cuda or to Thrust. No way. If you try, you have a linking error. So you don't want to try to help the compiler will figure out it for you. You don't want to help it. But for TBB you have, so it's kind of tricky. A key point here, once you want to enable the std_par, is to make sure that you don't have static allocation in your code, because the driver here, NVC++, needs to be sure that all the pointers on the CPU can have a mirror on the GPU. And if you have static allocation, of course, it's not possible. So that's, I think, you want to be sure. Even the most ridiculous static allocation you can have, especially if you want to use HDF5, because there is a lot of static allocation in HDF5. I didn't check the 2 yet, but we will check also that for the school. But for the 1, there is a lot of static allocation, so you want to separate the compilation to be sure that NVC++ will not be bothered by the static allocation of HDF5, because you don't care about HDF5 in the GPU. So you have to have a nice design also to be sure that everything is working. But for the computing, avoid static allocation. You do everything with vectors, typically. STD vector is okay, no problem. And everything is going on. So if you have a big code base, be sure that to pass through all your code to be sure that you don't forget one static allocation somewhere, otherwise you will have a crash, and it's could be hard to debug, in fact. So be sure that everything is nice. So in terms of memory management, as I explained before, so for classic Cuda or classic thrust, without the thrust universal vector, of course, you have some data in RAM, in CPU memory, and then you do your data copy, and you can access the data on the GPU. Of course, if you forget, you have an error, it's horrible, and you have to figure out what transfer you forget. Then we have unified memory for NVC++ and NVFortran. So we already talked about NVFortran, but for NVC++ it's the same. So here we have data on the RAM. The GPU wants to access this data, but the data is not present on the GPU memory. So there is an error, but driver catches the error and then performs the copy for you. So it's really nice. Depending on the volume of the data you want to transfer, could be better to explicit the transfer, but for really simple kernel, simple lambda function, it's really efficient. So you can start with it, and then if you really have a problem of performances, typically if you see that with Nsight, go for an explicit data transfer with Rust, for example. It's okay. So if I do my Adama product with my Nsight here, with the timeline here, so you recognize what's going on here on Cuda here. You have Cuda API. So if I zoom, you recognize the page fault, host to device transfer. So here I have a page fault, so the error I mentioned just before. So I have a page fault, and the driver will say, okay, there is a page fault, but there is some transfer missing, and here is a speculative prefetch host to device transfer. So we will speculate, okay, maybe the user wants this data, so I will transfer this data, and for the next part, I will have another page fault, and I will have another speculative prefetch during the execution of the kernel, of course. So this can slow down the first execution, because the first execution of the kernel will be a bit laggy because of the transfer, because there is no data on the GPU first. But after that, everything will be quite fast if you have several cores. And here you recognize thrust, of course, because under the hood, NVC++ we call thrust, and cube under the hood also under thrust, if you want to have a look. If you know how to deal with thrust, you do automatic GPUification with STD transform. Everything will be nice. So STD transform is okay for triadic, as I said before. So X plus Y, for example, it's a triadic. If I have a quadratic computation to perform, it's quite annoying. It's not really well managed right now. So we can do a classic C++ for loop, but of course you cannot use it on the GPU. And if I use an STD transform, I can use a dedicated vector of index, as I said before. So I pass my vector by copy. So it's important to have a vector by copy, because the driver will copy the data for you. You don't have to do that yourself. But it's okay for the GPU. Work well, really, really well, in fact. You need an extra index table, so it's not that elegant. But the good point is it's really close to Cuda kernel. So if you have a Cuda kernel and you want to convert the Cuda kernel inside Lambda, you say, okay, I pass my index in parameter. So I do my STD transform or my for each with my index, and I get my index, my thread index, if you want, on my Lambda, and then I can call my vector as before. So they are caught by copy here, and so I perform the copy once, and then normally it's okay. So you can do that. It's not really elegant, but for now it's difficult to do better. So if you want to do some thrust, it's more powerful. But for the classical STD transform stuff, the zip is not that good right now. So we have to wait a bit for that. And we still have an hope for C++23, but it's a bit too in the future right now. So I can do a Cartesian product, for example, for iota views. So I can compute, if I have A and B, for example, I can compute the view of the Cartesian product of from 0 to n and from 0 to m, so to have a full matrix of Pierre here. And then I can iterate for my index, unwrap my index, and do some computing here, transpose. Why not? It's possible to do that with for each. In the future, it will be possible to do that with a parent sec, and everything will work on the GPU. For now, it's quite difficult to do it, but it will come at some point. So the index could be multidimensional. It's really powerful. So you are not limited to 3 dimensions. You can have more if you want. No problem. There is no need for allocation. So you don't have to have a full table allocated on your GPU just to manage index, because it's a bit of a pity because you waste memory just for that. Not really elegant. But if you want to broadcast, we can do much better in C++23. You can use broadcast this way. So with STD view join, STD views repeat. So basically here I have a vector B. I repeat the vector B infinitely. So I get a view to repeat the vector B infinitely. And then I iterate with my STD transform on my vector of A, which has an end, in fact. And the vector, the extended vector B does not have end. So of course you don't want to iterate on that. You want to map it just after that. So I map this one, I map the vector result, and then I can perform my broadcast. Everything is okay. It's not vectorized yet. It's not parallelized yet. It's really tricky, in fact, to make it work. I asked some people from the standardization committee of C++. It's not that easy to do. And you can do that since C++ 13. So if you want to have a look, but it's working on G++ 13 and more, but you cannot really do some GPU computation with it, but it will be really powerful at some point when it will be available. So once you want to compute, at some point, as I mentioned before, you want to transfer your data from the host to device and from the device to host. So classically, you can compute and then you transfer your result, for example, if you do some simulation, and then you recompute and you retransfer. And of course, this is not efficient. So you can do all the computing before and all the transfer after, but it's still not efficient, of course. And what we want to do is to do something like this. So I do some computing and then I transfer my result, and I do some computing at the same time. I transfer the result of the previous computing, etc., etc. And if I have less computing, so maybe it's a bit of pity, because of course I cannot do 2 transfers at the same time. So it depends on that, but I can mitigate the problem if I do that. So how to do that? So here it's Aubert, but let's try another thing. So if I use my Adama product with asynchronism, so I still have to tell, okay, it's global, so I execute it on host or device. I have also to figure out the limit, so I check the boundaries. If I get my index, I'm out of the number of elements. I don't want to start the kernel, otherwise I will have a segmentation fault on the GPU, which is quite difficult to catch and very difficult to debug. And then I want to call the kernel. So the kernel is practically the same as before, just I have a if to be sure that I do not compute random value which are not belonging to the vector I want to perform. Then I want to call my kernel. I want to launch my kernel. So here I start with my block size computation, as I said before. Then I want to use a vector of stream. So I will use a Cuda stream. We'll see that a bit later. So I have a vector, I put all my stream in a vector, and then I have a vector. I can use the vector as I want. I assume here, of course, my number of elements is a multiple of the number of stream I have, so number of chunk here. Otherwise, of course, there is the last one, the last part, which is a bit smaller than the other. It's quite annoying to deal with. Let's pretend it's a simple example. And here I have my chunk, so I can iterate on my vector stream, and I start the copy from host to the device for each stream. So I start the copy with Cuda memcopy async here. So the same version of Cuda memcopy, but with in sync version. So I can pass a stream as an extra parameter if I want. And normally I can start all the transfer. So here I say, okay, I don't want to wait for the GPU to perform the mem copy. I just say, okay, I want this to be done at some point, do whatever you want. I move to the next thing I want to do. So then I can start my kernel. So 0 is for the shared memory, and here you recognize the vector of stream, so vectstream I, so I get the ith stream on my vector, and I do the offset, which is okay to perform my computing with the right data, of course. Because if you have two streams which are overlapping, you have threads which are overlapping on the memory, and you will have a mess. So you don't want to have that. And then, of course, I can do the same. I can do the data copy, device to host. So here I get back my results, and I do my Cuda memory memcopy async. So again, I say, okay, I want to do the copy, and at some point I will do a synchronize, but for now it's not mandatory. And finally, once I want to call this function, I can say, okay, let's allocate the data on the CPU, but with a Cuda malloc host. So you pin the memory. It's really important if you want your stream to work. If it's not pinned, you will have a problem, and nothing will overlap, and you want it to overlap. So try to be sure that you use Cuda malloc host. Then I initialize my values on the CPU. I do some Cuda malloc on the GPU. So classical allocation on the GPU, no problem. Then I create the streams. So I create my vector. So it's a type def. So it's a STD vector of Cuda stream, and I put that in a vector stream. So I'm not bothered by the naming here. Then I call the kernel launcher I just showed. I do some repetition, some computation repetition to be sure that I see what's going on. And then I free the data on the GPU. I free the data on the host, on the CPU, with a CUDA free host, because I did a CUDA malloc host, so you want to be coherent. And finally, I destroyed the streams, and I can also print the result if I want. It's totally possible. So if I do that, and I have a look to Insight, so you recognize all the streams. We have 4 streams here in these examples, just to see what's going on. So you recognize here the copy host to device, which is not really asynchronous, of course, because you have a big copy to do. So a copy cannot be done twice. Depending on the GPU, some GPU you can copy from host to device and from device to host with 2 channels at the same time. For this one, it's not possible if I remember well. In fact, it's one direction, so it's not cannot do much than once at a time. Then we have the kernels. So I execute all the kernel here, and the kernel normally do not overlap also, because once I use a kernel, I use a full GPU, so I cannot have a parallelism opportunity here. And finally, I have my copy device to host. And here the good news is, here you have a small overlap. Oh, of course, it's a small overlap because it's an Adama product. So it's not that big of a computation, so you cannot overlap much. But here you see that I have my first, my last kernel here and my first memcopy here. And during this memcopy of my thread, my stream 13, I do my last computing of my streams, so 17, 16, and 14. So everything is overlapping here. Not this one, of course, because it's the same stream, but the other one has overlapping. And you have also to be sure that you have a color. The color is not the same as a classical allocation, malloc allocation on the host. So you be sure that if you have this color, you have a pin memory. So the green, flashy green here. So this means that you allocate your data with a CUDA malloc host. If you do not do that, you will have no overlap at all. And here it will not be pink, it will be red. So to tell you that it will be green and red and not flashy green, light green and pink, to tell you that, okay, you did not use the right CUDA malloc host. So only for the allocation. Here, even if you call the asynchronous copy, you will not have this in pink. You will have this in red to tell you that you forget to do the proper allocation to be sure that the memory is pinned to ensure the stream will be efficient. So here's another example with a lot of kernels. So I have my kernel running here, my memory in several directions at the same time, as I said before. So I can put data on my GPU. I can get my data back at the same time, depending on the GPU. Again, you have to check the datasheet of your GPU to be sure that you can do that. Normally, it's quite common right now if you have A3000 stuff like this. It's possible, but always check if you have a small GPU on your laptop to be sure that you can do that. And here I have my kernel. So here only one kernel. I just try to have one kernel, but to overlap only the transfer, it's possible. And before it was several kernel and several transfers at the same time. So do not forget the CUDA malloc host and the CUDA free host if you want to be sure that you want to have several streams, and the CUDA memcopy async and the kernel. So you have the grid size, the block size, the shared memory pointer if you want to use explicitly some shared memory inside your kernel, and the stream you want to use to start your kernel, and everything will be okay. And you have normally the same stuff in Fortran if you want to do some wizardry with Fortran with that same library. So then the last part will be about CUDA graph, because I will not enter in the detail of the implementation because we don't have time, but just to give you an overview of that. So with my classic kernel launch, if I have several kernels to launch, I will be on the CPU, launch my first kernel. My first kernel is done, so I go back on the CPU, I launch my second kernel, etc., etc., etc. It's quite costly. And it's not costly about data transfer, stuff like this. It's costly because starting a kernel takes time, a bit of time, because you have to start the kernel, you have to make everything rolling. So it's quite costly, especially for small kernels. So what you can do with a trivial graph launch is to say, okay, let's put all the nodes in the same graph and start the graph once. So you have one graph launch, and then you have all the kernels running after each other in the same call, and then you fall back on the CPU, but all the kernel are called, so you don't pay the starting of the kernel each time you want to start your kernel. So if you have really small kernels, it's really efficient to do this one. Typically, our Damar product, it's a really small kernel, so normally you should be able to do that if you really want to optimize it. Then, of course, it's a graph, so you can have a graph of kernels. And you can say, okay, maybe my kernel B and my kernel C can run together, or D and E, for example. It's possible, no problem. So as Stephen Jones mentioned a couple of weeks ago in the GTC, it's not always the case. It's a parallelism by opportunity. So maybe B needs too much threads compared to C, and C cannot have enough threads, so they cannot overlap, or maybe they can, or maybe D and E are the same. So if it's possible, the hardware will do that. If it's not possible, you will not have the parallelism. So you have to check with Insight to be sure that, okay, how many threads I need for this kernel? Is it okay? Is it enough? Compared to the maximum number of kernel I can launch on my GPU. So you have to check that to be sure that everything is okay. But here you can have, in the best case possible, you can have extra parallelism here, which is really nice. And you can express more parallelism on your computing, which is the purpose. In fact, once you do some GPU computing, you have a lot of parallelism to express. And here you can express more parallelism even. But there is a problem with, in fact, there was a problem with CUDA graph, because if you have iterative algorithm, you fall back in the same problem. Because you say, okay, I have a while loop, for example, to to do my iterative execution. I start my kernel. Okay, my Cuda graph is really efficient, but then I fall back on the CPU to say, okay, is it finished? No. Okay, I have to restart my graph. Is it finished? No. Okay, I have to restart my graph. And this is really annoying because you have to pay the starting of the graph each time, which is not really nice. So you can now put the while loop inside the Cuda graph, and you can start the loop on the GPU. Typically, if you want to have, I don't know, a QR decomposition, and you want to loop until you get the precision you want, so not a fixed number of iterations, but a stop condition, you can do that. And you can say, okay, I can start the graph the number of time I want, and I stop until it's finished. So you pay only once the graph launch, and then you iterate. And once it's done, it's okay. Really powerful. And of course, once you have a graph launch like this, you can have a node which is composed of a subgraph, in fact. So you can have condition also with if statement. So we can say, okay, if it's true, then I want to start another graph. If it's not true, maybe I want to do nothing. And again, you have comparison by opportunity. So maybe B will be small enough, and P and Q and R can start together, and maybe it's not enough, so maybe it's only B and Q, and then R will wait a bit. It's possible. And of course, you can do that many times, as much time as possible. And you can also reuse the nodes that you want. So if you define nodes to perform, you attach a node to a kernel, classically, and then you can reuse the kernel depending on the strategy you want. It's totally possible, no problem. So it's okay, of course, if you want also to start QFFT or Nickel or Mishmem or library like this, so Kublas, etc. So they can be used inside the Cuda graph. So it's automatic recording stuff. So you can pre-record your graph by pretending that you are calling all your function, but just to create the graph, and then you call the graph, and it behaves as you were calling the function before. So typically, if you want to do some QFFT, it's really, really powerful if you want to do that. So since Cuda 12.4, you can do that. So normally it should be okay for everyone now. So if you want to have a look, it's really powerful. And it's also possible to use several GPUs with one graph. So Stephen Jones mentioned that a couple of weeks ago, as it was trivial. In fact, I didn't know that, so I will check. Normally, it's possible. And once you create your graph with streams. So you can pick one stream and say, okay, my stream belongs to this GPU, my stream belongs to this one. And normally you can build your graph like this. Maybe there is a more easy way now to do that. So we'll try to do that on the school. Could be nice. If you have some question about that, of course, if you don't care, maybe we can spend time on other stuff, but this is really powerful. So to conclude, well, I'm right on time. So we get really good performances on GPU with Cuda, of course, and with NVC++. So if you want to compute directly C++17, C++20 is not really well managed right now, so you have to wait a bit. So I test with HPC SDK 24, 25. Now I'm testing with the 26, so everything is really nice. So do not link explicitly with Cuda or with Thrust if you use NVC++. NVC++ will do the magic for you. If you want to target specific GPUs with Cuda visible devices, it's okay. It's working, no problem. You have to avoid static allocation to be sure that everything is working. Otherwise, you will have strange Cuda error with invalid pointers, unreachable pointers, stuff like this. So you have to be careful about that. And of course, since everything keeps upgrading, now it's not possible to use K80 with NVC++ or NVCC, and other GPU will die gently on the road because it's 11 years ago, K80. So of course it's a bit longer. So you have to take that account also if you want to renew your GPUs on your favorite computing center or for your laptop or whatever. And thanks for your attention. If you have some question, I will try to answer them all. And while you have a bit of time, so let's see. Oh, there is already some question. Okay, so question from David. The thrust universal vector knows about the underlying architecture and avoid copies when we have unified memory. Normally, yes, I checked that with the 25 HPC SDK, I think. It was working. So it's handled under the hood by the driver. So normally should be okay. At least for what I check, it's okay. Maybe in your particular case. In fact, it depends. If it's unified memory by software, it's okay. If it's unified memory by hardware, normally it's okay also. But I don't have Blackwell or Aubert to play with right now. So, but normally should be okay. In the documentation, it's supposed to be okay. Question from Salah. Thank you for this important event. Okay. Thank you, Salah. Question from Ahmed. Is it efficient to associate CPU threads with GPU streams when launching a large number of kernel from CPU? What is the overhead? You have a special mode for that because normally, if you want to start some kernels, you only attach one GPU to one thread on CPU. And if you want to attach more, you have to tell gently the hardware to enable a specific flag to say, okay, I allow several threads to do the GPU stuff at the same time. I never play with that because it sounds not really trivial and natural in documentation. So I prefer to stay with one thread dealing with full GPU, and you have enough work to do to deal with one GPU. I'm not sure you can diminish your overhead if you have several threads because you will have I guess a lock at some point. So maybe we have to check. Maybe depending on your problem, the one you want to solve, but maybe would say. Regarding documentation, I would say maybe it's not that useful to try to handle one GPU with several CPU threads. But maybe depending on your problem, maybe it's okay. But for everything I checked, one thread is really worth it, so no problem. Yeah, and the overhead, yeah, will be normally we will have a lock at some point. So David is happy. Question from Maxime. Thanks for the presentation. When setting number of blocks, don't you need to take account the memory size limit of the block? Yes, you have. I didn't mention that also, but you have limit in the shared memory. You have a limit in the number of registers you can use. Maybe I can show you here. So I performed that little discovery on my laptop. And so here you have the limit, so texture alignment, we don't care. Yeah, here you have the limit of the number of registers available per block. So the full block, not only one thread, the full block. And so here you want to be sure that typically if you want to enroll and to do some kernel merging and stuff like this, you want to be sure that you don't use too much registers, otherwise you will kill your performance. So you really have to do this kind of discovery properly to be sure that everything will be nice. So you have the limitation here, of course, in terms of number of threads, but you have the limitation of memory here. You have the full memory of your GPU, and you want also not to exceed the memory of your GPU, otherwise you will have a problem. And you have also the limit of the shared memory. I don't remember where you have the constant memory here, and extra memory, and normally the shared memory, or maybe I forget to print the shared memory. Of course. That's always what happens when you try to demonstrate something. Okay, there is also a limit of shared memory per block. Here, you have the limit of shared memory per block, so you don't want to exceed this memory if you want to have fast access. You don't want to exceed the memory of constant memory also if you want to have fast access. You don't want to exceed the number of registers you want to use, but it's generally for the total block here, not on the thread, but you have to extrapolate that for all the thread you are using to be sure that everything is nice. And if you have special case, be sure that in the worst case, you don't have maybe two warps which handle the same special case on the same on the same block, on the same streaming processor. Otherwise, you will have a problem also. So yeah, you have to deal with that properly to be sure that everything is nice. So yeah, there is a memory limit. So, and depending on the type of the memory you want to use, you have different limits. So you have to deal with that also. So Hamid is happy. A question from Maxime also. So thanks for the answer. When using unified memory, doesn't the error catching mechanism introduce overhead? Yes, there is an overhead, of course. There is an overhead. So I don't remember the values, but I can check for you for the next time if you want. But generally, if it's a really big transfer, you prefer to do that by hand and explicitly do the transfer, because otherwise, as you saw in the slide for the insight, you will have a lot of chunks with there is a segmentation fault. Okay, I do the transfer. Oh, there is another segmentation fault. I redo the transfer, etc., etc. So you have an extra cost each time because the driver will figure out, okay, it's not done yet. I have to redo the transfer automatically. So if you have a lot of data to transfer, if you do it manually, it will be much more efficient. If you have small data to transfer, one kernel, stuff like this, normally it's okay. There is some figures, there is some values, amount of memory. It's I think it was don't know the value by heart, but something like a couple of megabytes. It's okay, no problem. If you reach I don't remember how much 100 megabytes, then it's better to do it yourself. If you really care about the data transfer, because data transfer represent a huge impact on your performance, you want to do it yourself. Of course, if the data transfer is a bit long, but you have really big kernels after that, maybe it's not a problem. But if you profile and you see that your data transfer could be a problem, yes, it's better to do explicitly the transfer. And normally there is also another trick for Hopper with a decorator in Thrust. I forget to mention that. If you want to do some Thrust with Hopper, you can explicitly in your Lambda or in the call just before your Lambda, so you wrap your vector around a function, I don't remember the call, to tell the kernel to use the TMA, so the tensor memory accelerator you have explicitly in Hopper or not in Ampere, for example. So you can do this kind of trick also if you want. So yeah, you have overhead. Another question from Maxime. So isn't using Cuda graphs on an entire algorithm risky? I didn't show you the code, but this is horrible. It's for me, it's quite not the same level as Vulkan, because Vulkan you explicit everything, but you have to create a node graph for all the kernel you want to call. You want to wrap the values that you want to call. You want to put that in a graph. You want to do the edging between the graph to be sure that everything is nice, and then you want to dump a dot. So a graph in a dot format to be sure that you did what you think you are doing. So yeah, it's risky. For me, if you have a pile of kernel that you know, and you know they are working, you can maybe try to do a graph. But start with something working first, because I never debug graph. Generally, it's what I do every time. So I try to do something without any debugging. So I put everything to be sure that I can debug if I want, but I prefer not to. So I never tried also to debug a graph from time. Normally should be really better now because Insight is evolving in new versionings, which could be much better. I thought that Cuda graph work best for Cuda operation only. Yeah, if you do QFFT, I did that with QFFT and with QBLAS also. Another point which is nice with Cuda graph, in the same for GPUification, once you have better performance even on CPU, is once you try to do a Cuda graph, you have to think, okay, which kernel I want to execute at the same time of which one, what is exactly the dependence, and not the lazy dependency because I just want to execute everyone, but the real dependencies of my kernel. And then you can also have some tweaks and said, okay, these kernel are supposed to be parallel. So maybe if I decrease a bit the number of threads for all the kernels, maybe they really work in parallel, and maybe it's okay. So you can have a nice step back on your code to say, okay, maybe it's okay. But for example, yeah, I did the Cuda graph implementation for Grayscott. So to have something interesting, I did the implementation with Laplacian, so the implementation that Vincent mentioned already in his previous talks. So you compute the Laplacian of the U species and the Laplacian of the V species, and you try to do both at the same time, even if you can do both really faster. So after that, it's a trade-off. You have to play with it and say, okay, for this particular GPU, this configuration is better. For this one, this configuration is better. So it's a lot of playing. In fact, you have to play. You have to feel what the GPU is doing. Say, okay, maybe I have too much threads. Maybe I have not enough thread. Maybe I broke my my memory. I broke my number of register. So you have to play. It's again, it's always a playing matter. So, yeah. Okay, question from David. Since NVCC is not up to date with the latest C++ standards, but we have 23, 26 is not there yet. Is it possible and is it a good practice to use GCC Clang for CPU dedicated part of the code and compile Cuda kernel for GPU dedicated part of the code with NVCC? Yes, I do that already. It's really, really powerful. In fact, I do that for the school because, as I said before, if you want to do some magic with NVC++, for example, for the Grayscott, NVC++ will complain because of HDF5, because of all the constant table in the HDF5. So you have to split that and say, okay, there is one library compiled with G++ or Clang++, your favorite compiler, no problem. You compile that for the CPU and everything is okay. And then you do the magic with a different library and then you link in your final executable. It's way more better to do that. Yeah. And for debugging is better. If you want, also we will address that also in the school. If you want to share your product, you want to share your program, and you want to do a nice packaging. Of course, you want to do a package with Pixie, typically, thing like that. You don't want to have a big mess and everything in it. You want to have small pieces, and then if you want to specialize your computing part for Intel, for ARM, for whatever you want to use, it's okay. But you don't want to specialize everyone. All the HDF5 you don't have to be bothered with vectorization. Except if you have some filter, but I'm not really sure. It's normally it's already handled. If you want to manage, I don't know, configuration, argument parsing, you don't need vectorization for that. You put that in a really nice small library with not too much optimization option because you don't care. And the more optimization you put and the smaller compilation gets, of course, and you want to pass time on the compilation on the things which matter, not on the parsing of the argument that nobody cares about. So splitting everything is a nice way to do, and we are obliged to do that for the C++ part on the school because of the limitation of NVC++. And also, yeah, I have some tricks for the pyramid algorithm to be sure that it's working with C++20 for the CPU part, but also with C++17 for the GPU part, because they are not totally aligned. So another trick to do. But yeah, it's really nice to split. Way better to split. And yeah, once again, things to Sebastian. If you split everything, you have a nice design. If something go wrong, you can change it. If your boss said to you, okay, you have a nice Cuda implementation, but I don't care, I have an AMD GPU for the client, okay, change your backend. Not recompile everything, just change this tiny library to do the computing you want, and you're done. And if you do that with a type def, as I mentioned at the very beginning of the presentation, normally you can do the change before your boss leaving your office, and it's really, really nice for you. You get points for that. So we have a bit of time for a couple of questions also, if you want. Oh, question of Hamed. So during one of my previous works, I have tried to synchronize all GPU threads directly from the GPU, but it seems that Cuda device synchronize can only be called from the CPU. Yes, maybe this limitation has been addressed in newer version of the toolkit. You have synchronize, but it's not a Cuda device synchronize. You have I think it's __ thread synchronize or synchronize. Just you can call that in the kernel itself to synchronize a block, I think, if I remember well. We don't need that in Grace code, so I have to revise a bit. But yeah, for the block, normally you should have an __ thread synchronize. I think the name is this one, to explicitly say, okay, all my kernel, I want to do this step, then I synchronize, and then I continue. You can do that inside the thread, so it's better because you don't have to call a kernel, a small kernel, and then do a synchronize and then recall another kernel. So you can do that directly in it. So yeah, you can do that. Maybe this limitation has been addressed. So yeah, it's not really addressed. It's not the same function, but you can use it. Since documentation mentioned host device function. I never use a Cuda device synchronize inside the kernel because there is another function for that, but maybe now it's working. But normally the Cuda device synchronize works for the whole GPU. And maybe you don't want that. In your kernel, maybe you just want to do one part, and then you wait only for the block, and then you do another part. Because normally the kernel is supposed to deal with particular data, and if they are synchronized, normally you don't need to synchronize everyone. You just have to synchronize this one. So maybe it's also a question of rewriting your kernel, but normally you should have a solution for that. Just want to be sure that with the Cuda graph example, with the while loop, you have shown you don't have this type of issue. Normally kernel are the same kernel, so if you do some magic with synchronization inside your kernel, the synchronization should stay. It's just another way to deal with how you start the kernels, but normally should be the same. I never try with the synchronize inside a Cuda graph, but normally should be okay. Okay, Ahmed is happy. Thank you, Ahmed. Okay, thank you, Marie. So okay, maybe it's time. Yeah, we are on time. It's really good. So of course we will dig into the detail in the school, all the implementation. So if you have some question regarding the implementation, you can have a look. We'll have a look in the school directly once we will dig into this weird detail. So normally, if you, oh yeah, maybe a point also, because I have a lot of this question right now. If you want to attend the school, but you are not really sure if you can follow the school because 2 weeks it's a lot or stuff like this. If you watch the webinars and you can follow them without problem, normally you will not be lost in the school. If the first minute of the webinar you get lost, maybe this will be a bit tough, and maybe you prefer to watch it carefully, maybe on YouTube remotely, just take time and get the information. If it's okay for you to follow the webinar and to get the information, you can attend the school, no problem, you will not get lost. And even if we push further, of course, because it's a school, it's a technical school, in fact. So of course we push further, but here, if you get this, everything will be nice for the rest of the school. And of course, it's the same for Fortran. It's the same for Python. In fact, Python is not right now, but a bit 2 weeks from now. Normally, you get the first Python talk. So thanks everyone for attending this webinar today. So don't forget to register if you want to attend the school, and don't wait too much to register if you want to attend the school in Annecy, because there are a lot of people who want to have apartment and to have hotel and stuff like this, so it will be quite difficult. If you are interested in all this wizardry, next week we will do wizardry with Kokkos on CPU. So we go back on CPU and then we will go back for Python week after. So next week, Kokkos. So a new library we use in the school. So how to install it, how to use it, what is the difference with Cuda, with SYCL, with all this kind of stuff. So really technical presentation, of course. That being said, thanks for coming and see you next week. Bye.